Welcome, everyone. Today we'll have the pleasure of hearing from our very own Sasha Chernoglazov. He's a graduate from the prolific plasma physics program at the MIPT. He recently got his PhD from the University of Maryland, where he contributed to a severe overdensity of Sashas. He's worked on a variety of topics in plasma astrophysics, from relativistic jets to both kinetic and magnetohydrodynamic turbulence. Today we'll get to hear about a topic very near and dear to my heart, pulsar magnetospheres. So please, Sasha, take it away.
Thank you, Alex, for the introduction. Thank you for coming. And today, as Alex said, I'm going to speak about kinetics of collisionless relativistic plasmas, which we have mostly in the pulsar, in the magnetospheres of the pulsars. And while I'm pretty sure that everybody knows here, so this is the outline of my topic. First, I'll start with some short introduction, because I guess most of you know what the pulsars are. Then I will cover different regions of the pulsar magnetosphere, which are responsible for the different mechanisms of the emission, or different energies of the emission, which we observe, starting from high energy emission, coming probably from the magnetospheric current sheets. Then I'll focus more on the inner part of the magnetosphere, on the polar discharge, which fits the magnetosphere with some QED-produced plasma. And then I'll try to illustrate how these processes happening in different parts of the magnetosphere might be responsible for the production of extremely energetic, recently observed emission with the energy range of like 20 TeVs. So the pulsars were first discovered in 1967 as the very regular, very stable bursts of the radio emission. And the bursts were that stable that the most natural explanation for this burst was proposed that this is little green man. And the first signal was called LGM1. But they were quickly associated with rotating neutron stars, which are the massive objects with the masses from 1.5 to 2 solar masses, doing up to thousands of revolutions per second. The fastest non-rotated pulsar probably rotates like 700 rotations per second. And we see the burst of the radio emission when the beam of this emission comes towards us during the rotation of the pulsar. All of these pulses are very unique in some sense. This is the examples of the observed pulsars one by one, and I guess this is pretty famous figure from like the public culture and some music albums. And while each of these pulses is unique, the average of hundreds, even thousands of these pulses is very stable and sort of unique for the pulsar might work as its fingerprint. But something is powering this emission, and where this emission might come from, this is what's say that the pulsars are rotationally driven emitters, which means that if we measure these pulsars, as I said, they're extremely stable and they emit in the period of rotation. But we can observe that they slowly spin down, or their rotational period increases. Here's the example of the measure of this linear increase in the period, which is observed over the time scales of the days that is here on the x-axis, and the shift is measured in nanoseconds here. So this is tens of nanoseconds in the during like thousands or hundreds of thousands of the rotation. This is the per pulsar, which is doing 30 revolutions per second. And according to the classic mechanics, this means that this rotational energy is taken away and probably re-emitted somehow in the form of the electromagnetic emission. How this happens? So this is, and if we combine all of the known pulsars which we observed so far in the different energy ranges, most of them are radio pulsars, but some also observed with the gamma emission, but still they emit radio. On this p dot diagram, which has the rotational period in the x-axis ranging from 10 to the -3 seconds to like 10 seconds, and probably even 100 seconds. Some recently observed and yet debatable objects, and they're spin down. We can see that there is no pulsars here in this low energy range. So if the pulsar rotates very slowly and emits and spins down very slowly, probably it releases too little energy to produce the observable radio emission. And the mechanism how this emission might be, how this rotational energy might be extracted and converted into electromagnetic emission is associated with what is called magnetosphere, or the inner, close to the neutron star outer zone, which is penetrated by a very powerful magnetic field, which correlates to some sense with the neutron star. And it was pretty quickly released that this rotational magnetic field should create the electric field, which extracts some plasma density from the star surface and populates the magnetosphere. This charge density is called the Galdrag-Julian density, or the minimum charge density, which is needed to screen this, or to compensate this gravitational electric field. And it is electric field, this charge density is small in the sense that it's still the energy density of this, the region is still dominated by the energy density of the magnetic field, which can be determined by this parameter sigma, or the magnetization, which is the ratio of the magnetic field energy density to the rest mass energy density. And this population of the magnetosphere with plasma has two consequences. The first one, the extracted charge propagates through the magnetosphere and creates the magnetospheric arc, which twists a bit this magnetic field lines, creating the toroidal field, which is shown here in the arrow. And the second one, the magnetic field, which is supposed to be anchored by both ends to the neutron stars, cannot correlate beyond certain radius, because where the gravitational speed of the plasma, which is connected to magnetic field lines, would exceed the speed of light. And this surface is called the light cylinder in here. And all the field lines which cross this light cylinder start changing their geometry and open up to the infinity. While the field lines which do not cross this light cylinder organize the closed field line zone, and we won't talk about this one, is not interesting happens there. All the magnetic field lines which are open, so to cross the light cylinder, are anchored to the surface of the neutron star in the region which is called the polar cap. And this is just the definition. And now we have the toroidal field and the rotational driven radial electric field, which means that we have a Poynting flux, which takes away the energy from the magnetosphere and brings it away. And this electromagnetic energy is re-emitted in the different energy branches of the electromagnetic emission, starting from radio. For example, it's shown here, one of the spectra with the energy range 1 gigahertz, which is shown here, like hundreds of megahertz. This is around 10 to the minus 6 electron volts. And up to the gamma emission, gamma rays, which is in the range of tens of giga electron volts. And even higher, as we discuss later. So to understand where the different emissions, which I mentioned, come from, we can look at the phase resolved, the light curves, the different energy ranges, where the first plot shows the phase resolved radio versus the radio emission for two rotational periods. So the first burst is here on the H, and the second burst is exactly in the center. And the other energy ranges, it's from optical to hundreds of MeVs. As we can see from here, they allocate the different parts of the phases of the light curves. And probably these narrow beams of the radio emission come from the inner magnetosphere, or the inner zone of the light cylinder close to the polar cap, and somehow associated with the plasma discharge, which I will discuss in the second part of my talk. While the high energy emission, which is much broader and has this broad bridge emission, probably comes from less isolated zone, which is associated usually with the current sheet beyond the white point, where the magnetic reconnection happens. And I know some of you will like this information from Wikipedia page. This is just a reminder that the magnetic energy, which is transferred to this field line, to this zone, is released and transferred to the particles. So the particles are accelerated, and somehow they re-emit this energy, creating the observed electromagnetic emission. How this might work? The conditions of the light cylinder of the pulsars have so high magnetic field and probably that energetic particles that the synchrotron cooling of the particles becomes important in the production of the synchrotron emission. So this is the outer current sheet, which is probably responsible for this emission. And as I further will try to discuss how this synchrotron cooling might be produced and what is the radiation imprints of this cooling and of this emission. I'll need to introduce what is called the radiation reaction limit. So as we know this, the reconnection drives the global electric field, which makes the plasma drift into the reconnection region. And if we look at what is the radiation force or radiation reaction force, which slows down the particles, it can be balanced by acceleration in this electric field. And if these two forces are balanced, this is radiation reaction limited regime, which is parameterized by what is I will call gamma sin or radiation reaction limited Lorentz factor. So I will use just gamma sin because it's shortened. And it might be just compared to the magnetization of the upstream, which is this is two-dimensionless numbers. If this gamma sin is less than magnetization, which probably means that the cooling becomes effective at very early stage of the evolution of the particle, I will refer to this case as a strong cooling. And the opposite case would be the weak cooling, when gamma sin is larger than sigma magnetization. Okay, here we come to some of my results. This is the simulation setup which we studied of the isolated current sheets with a particle and cell simulation. So this is collisionless relativistic plasma, where we ran the relativistic current sheet with magnetization of the upstream around 50. We cannot go larger because we need some large separation of scales. And we ran it for many light crossings to reach the steady state, which required us to supply some fresh plasma and magnetic field in both upstream zones of the current sheet, and also get rid of the reconnected plasmas with the outflowing boundaries. And on top of this, I varied the efficiency of the cooling from 0.2, which is a strong cooling again, the ratio of the gamma sin to sigma, to about 5 or even infinitive, which means no cooling at all. And here's the typical.
You're not resolving the skin depth of the plasma here.
I do resolve skin depth.
You are?
Yeah.
How
So it's resolved by free cells for the cold plasma of the upstream. In this overdense plasmoids become worse, but there is still some acceleration of the particles, and the Lorentz factor plays its role, increasing the effective skin depth. So in the worst case, it's marginally resolved. Okay, and here, this is how the cooling might affect the typical imprints or the typical shape of the current sheets. So this one shows the density of volume rendering on top and the magnetic field on top of this, which are shown by these colored field lines, where the color represents the strength of the magnetic field. And note please that the color bars for these two plots are very different. So the color bars for this strongly cooled, more dense current sheet is like 10 times larger than the color bar for weakly cooled current sheet. And what we see here, that this structure pretty much resembles what we know from 2D. The typical 2D snapshot is shown here in the left lower corner. So we have the X points where the topology of the magnetic field changes. So it's pretty much here. And this is what was shown on this snapshot from Wikipedia page. We have the plasmoids, which are these massive flux tubes in here. And this is the reminder that these plasmoids accumulate the outflow from the X points and also mediate the reconnection rate of how efficient the reconnection is. But while here everything is very laminar and very symmetrical, here the structures has some additional features. For example, we can see that these plasmoids are like flipped or kinked. This is the additional drifting instability which develops in the perpendicular to the magnetic field direction. Or here there are these ripples, which are the imprint of this instability. This change of the geometry of the current sheet is probably determined by the properties of the particles, which accelerate in there or cool down in there. And here's the comparison to the typical spectra of the particles, which pass through the acceleration phase in this current sheet. And we can see that in any case, there is a very well-developed power law spectrum, which is pretty steep. And for the weak cooling regime, which are shown here in like reddish or warmer colors, it is pretty extended and pretty shallow spectrum, so it's pretty hard spectrum, which cannot extend further than pretty much the gamma sin or this radiation reaction limit. In the opposite, the spectra for the strongly cooled current sheets truncates at smaller energy, smaller Lorentz factors, but it can reach the Lorentz factors comparable to sigma. That's why we speak that. That's why I thought say that the ratio of this gamma sin to sigma is important. But somehow the particles can overcome this theoretical limit of Lorentz factor being equal to the Lorentz factor of radiation reaction limit, which means that there is some mechanism which accelerates particles probably more efficiently than the. And to understand how this happens, here I'm trying to trace the fate of one of the particles, of the typical particles which reach one of the largest Lorentz factors achievable in the simulation for the strongly cooled current sheet. And here on the left-hand side, I show the evolution of this particle during the lifetime, where it starts being slowly dragged towards the current sheet together with the host magnetic field line, which is shown in blue here. Yeah, I don't know how well it's seen. And then it passes through the acceleration phase in the X point, where it gains the Lorentz factor shown here on the right, comparable, pretty much comparable to the magnetization sigma. Then it evolves in the outflow from this current sheet and experiences multiple scatterings, so it's gaining and losing the energy. Then at the later moments, it finds the way to get accelerated to the highest Lorentz factor possible in this simulation, which is just above magnetization sigma. But then it collides with the plasmoid and gets trapped in there until the end of the simulation. On the video here on the right, I will show the evolution of the particle in the outflow region, so during this period. And the volume rendering shows again the density distribution, and the blue lines are the magnetic field lines which approach the position of the particle. And the rods which is sticking out of this sphere, the particle is the direction of the velocity. So what we see here that the particle is being dragged away from the X point, but simultaneously it experiences the scatterings of these ripples, the drifting instability, which I mentioned in the previous slides. And this leads to the losing and gaining some small fractions of the energies. And at later moments, this particle is dragged towards the plasmoid by the shrinking loop of the magnetic field and collides with the plasmoid and radiates away all of its energies as shown here for the plot of the evolution of the Lorentz factor. So now it hits the plasmoid, radiates away, and gets trapped into the plasmoid until the end of its life. What is might be important for the further discussion here that the direction or the orientation of this magnetic loop is in the plane of the upstream magnetic field. And this helps us to predict what would be the radiation imprint from the current sheet.
So where is the acceleration actually happening? Is it happening outside the plasmoid or inside the plasmoid?
The acceleration or the
acceleration of the particle, the heating
acceleration of the particle pretty much happens in the X point, so it's in between plasmoids. And when it hits the plasmoid, it radiates away the energy, at least for the stronger cooled current sheets.
So were you suggesting that sort of the initial acceleration happened at the X point, but then thanks to the drift gate, you have sort of additional secondary acceleration from some sort of
rather than
formulaic process?
acceleration. Yes, this is a strong cooling, so the particle has a very little freedom how it can move. And if it doesn't behave, so it develops some angle to the magnetic field and gets some particular momentum to radiate away and loses the energy. So the particle must move exactly along the field line. This is what answers the question, what would be the radiation rate for the energy. My next slide. So as the energy of the photons, the synchrotron produced photons scale as the squared Lorentz factor of the emitting particle. And also there is just a fact, a nice mathematical fact that the energy of the photon, which is emitted by the particle which moves through the upstream with radiation reaction limited Lorentz factor, would be 16 MeV. So this is already X-ray, gamma rays or soft gamma rays of the X-rays. And combining these two results, we can see that the most energetic particles can potentially produce the emission above the radiation, above this theoretical burn-off limit, which is 16 MeV again. And if the Lorentz factor can exceed the Lorentz factor of gamma C, which is indeed the case for the strongly cooled regime. This is this dimmed spectrum here. And if we see the angle dependent, so the anisotropy dependent distribution of the energy of the emitted photons, we can see here from the left part for the strong cooling, where the x-axis is the direction, it is cosine of the angle between the upstream magnetic field and the direction of the wave vector of the photon, and the y-axis is the energy of the photons normalized by the Bernoulli energy of 16 MeV. We can see that the strongly cooled current sheet can easily produce very hard emission, which exceeds this 16 MeV limit by a lot. While the weakly cooled current sheets are the particles which are weakly affected by the cooling force. They have more freedom to move, so the emission is not that anisotropic for the strongly cooled regime, but it's also reasonably weak, since it takes a while for the particle to lose their energy. And this statement that the strongly cooled current sheets, which are more realistic for the pulsar magnetosphere suction, are responsible for the harder emission, can be seen here on the plots of the radiation spectra for different cooling regimes, where again this red colors show the weaker cooling, and the more colder the color become, this is the stronger cooling. And how the position of the top or the position of the peak of this spectrum scales with tolerance factor, or with the cooling strength, sorry, can come from the assumption that the particles still cannot move above the radiation reaction limited regime, but this reaction is determined by the local properties, but the local geometry and the amplitude of the magnetic field, not the global one. And if we combine these results, first of all, we can see from this histogram that indeed most of the particles are below this theoretical line, which shows the radiation reaction, the radiation efficiency, which balances the typical acceleration. And these results combined show that the position of the peak scales linearly with the cooling strength, or the ratio of the gamma seen over sigma. Oh, this is inverse proportional action. And here is the example. This is the example how this emission can be distributed across the whole current sheet, or what we expect if we look at the current sheet and see how it emits. Here on the left and the right, we see again the same snapshot as I showed in one of the previous slides, or one of the first ones about the current sheet. So this is the weaker cooling, and the green color shows the total emitted power, while this bluish color show the energy, the emitted energy in the hard energy photons above the theoretical limit. So what we can see is nothing surprising in here. This fluffy structure on the left shows that the particles with the weakly cooled current sheets can be emitted pretty much everywhere, while the emission is pretty weak. So again, the color bars are different for the left and right plots. And none of this emission goes into the high energy photons. While for the strongly cooled current sheet, this is pretty much opposite. The emission zones are very concentrated, and most of this emission goes into the high energy photons, shown on the right. And these emission zones are sticking to the outer shells of the plasmoids, because these photons are produced by the particles which bombard the plasmoids and lose their energy. So this is the example how this strongly cooled current sheets can produce the observed emission for the pulsars. And here on the left is the recent paper by Hess collaboration, where they observed probably the most energetic photons from the pulsar magnetospheres of the energy range of 20 TeVs. So this bluish is the observations. And it means that the current sheet needs to work so the pulsar needs to work very hard. It's to work very hard to produce this emission. But first of all, you can see that this part of the spectrum is very similar to what I showed in the previous slide. So this is like the shape which can be produced by the synchrotron emission from this current sheet, the pulsar magnetosphere, pretty much in the light spin. If we play a bit with the numbers, we can see that this gamma sine, which is determined by just the global properties of the sphere, is around 10 to the 5. And using my linear formula for the energy of the photons, we can see that the required magnetization of the upstream, of the immediate upstream of the current sheet, so pretty much these two regions, need to be around 10 to the 7. And this is the good news for us, because if the most energetic particles, which can be accelerated in this strongly cooled current sheet, can reach the Lorentz factors comparable to magnetization, and this gives the energy of the electrons or the positrons around 10 TeVs. So this is good news for the energy budget, because these particles can upscatter the soft photons, whatever the nature of these photons is. And the inverse Compton produced photons would have exactly the energy of in the range of 10 TeVs and not higher. This is what is observed. But there is a small discrepancy here, because this magnetosphere is likely populated by the polar discharge, which happens in here, produce this very dense clouds of the secondary plasma, which is spread out across the magnetosphere and populates it with plasma. And these bursts of plasma are very high density in a relative sense. So they exceed the energy of the Galbraith-Julian density, which I introduced in the first slide, by a factor 10 to the 5, 10 to the 6. And after doing some math and naive understanding how the discharges work, we can get the expected magnetization of the upstream would be around 10 to the 5. And this is already worse news for us, because it's comparable to the required gamma CN factor. So this is a weakly cooled regime, which cannot produce that hard emission, the energy range of GeVs. And also the particles are not energetic enough to produce, to upscatter the particle, the photons, the energies of their electron volts range. And to resolve the discrepancy, we need to better understand how the polar discharge works. And this is the second part of my talk. And I will start with some explanation how this model is, what the current understanding of people, how this model works, which still might be changed a lot. So this is pretty much the works in progress. But the best understanding is that, as I say, there is a developed toroidal field by the current of the particles. But it's, yeah?
But could I just ask a simple question about the current sheet emission?
Yes.
These gamma rays are pulsed?
Yes. So this is what was shown.
Kind of,
Yeah.
and that geometry that obviously the lighthouse beam for the radio emission is clear, but how does this
So light
sheet produce pulsed emission?
For most of the pulsars, there is a misalignment between the rotational axis and the magnetic axis. And the position of the current sheet or its geometry is the equatorial plane for the magnetic axis.
So you also get the current sheet.
So yeah, for the rotating parts, it looks like this, and then it rotates, and when it goes towards you, then you see the emission. Otherwise, you don't.
Is this exactly symmetric so that you know it's a pure dipole, or can you measure the asymmetry between?
Outside, at the larger distances, it's all dominated by the dipolar field because it drops as the slowest one. What happens at the very surface of the neutron stars, this is what the deniers say that it's not a dipole. It might be like either shifted dipole or it might have some higher nodes. It's not prohibited. But this is what
Actually, well, I was curious if the TeV emission was pulsed at all.
Yes, and it pretty much resembles the shape of this one, of this high energy gamma rays, which probably means that they come from the same zone. But yeah, for the TeV emission, they count it like 20 for something like that. All the statistics is getting there.
Could the TeV just be produced by some other sort of inverse Compton process? And it is probably the inverse Compton process. Yeah, closest current sheet. Likely because the light curve resembles what we see for the other energy ranges. Yeah. The questions? So coming back how the pulsar discharge might work, and so yeah, there is a twist of the toroidal of the magnetic field lines, which is set by the flow of the particles in the first place, and also by the adjustment of the geometry of the field lines of the light cylinder. And this twist says the global distribution of the magnetospheric currents as it follows from the Maxwell equations. And if in some zone of the magnetosphere, which is called a gap, the density of plasma is that low
that it cannot compensate the magnetospheric twist or the magnetospheric current, the electric field starts growing in there, and this region might potentially have some parallel electric field which accelerates the particles. And the classical figure says that this electric field happens close to the neutron star surface, and it extracts the particles from the stellar surface and accelerate them to ultra-relativistic energies. I will show it a bit later. And this leads to the emission of the curvature photons because this particle propagates along the band field lines. And these curvature photons are very high energetic, and while they propagate through the magnetic field, they get converted into electron-positron pairs. And since each of the primary particles extracted from the star can produce lots of these curvature photons, and each of them get converted to the pair, we can end up with some energetic, some very dense burst of their pair production. And the good news for us is that the distribution of this magnetospheric currents, as I said, is set by the global geometry of the magnetosphere and can be pretty much just extrapolated or interpolated to the polar cap region. And this is the example for the inclined rotator, which is pretty much realistic for the pulsars, which I talked about, like Crab or Vela pulsar, with the inclination degree of around 60 to 75. And you see that the currents, these magnetospheric currents, can be both positive, which means that the extracted particles, this gradual density, place outward from the neutron star, and there is the zone of the negative current where the particles fly in the opposite direction. But in the amplitude of these currents is still pretty comparable to the current, the galvanized Julian current, which means that this twist is still very small and the field lines are pretty much colloidal ones. Okay, to illustrate how this all works, I show the main stages of the evolution of this polar discharge when it starts with from 1D simulation, which it starts with the formation of this gap or the region where the plasma density is so low that it cannot compensate the magnetospheric current and starts developing the parallel electric field, which is shown in the upper plot here. And this electric field accelerates electrons and positrons shown on the phase space here. So this is the log plot. So the beam of the particles here is around 10 to the 5, the Lorentz factor of the particles. And when the gap size increases and the beam accelerates at the higher energies, it starts emitting the curvature photons, which are shown in the black dots in here. This is the cloud of the curvature photons, which eventually get converted to the electron-positron pairs. These are green and red dots. And here, and since the plasma density increases, it starts screening out the electric field. And at the later stage, when there is a lot of plasma produced, it fully screens the electric fields, for example, in this region. But then the burst of the pair production, and the beam flies away, and the process restarts. And here's the example how the discharge operates for the different magnetospheric currents. And for the positive one, the information of the gap, so this is the electric field, the phase space, and the charge density, the plasma density on the lower half. So it produces the bursts of very dense clouds with the multiplicity or the ratio of the secondary plasma to the initial plasma density, reaching like 1,000, which flies away from the star, and the star here is on the left. While for the negative magnetospheric current, there is still pretty much the same behavior with a small change that now the production of the particles happens on the high altitudes, which is the upper boundary of the domain in here. And this discharge pushes the particles, the main clouds of plasma, towards the star, with only a low energetic tail, which is shown on the zoom in here. Low energetic tail of the particles fly in the opposite direction and end up in the outer magnetosphere, somewhere close to the current chain. So this all happens in the inner part. Yeah.
So what's the multiplicity of the reverse particle shower?
It's also thousands for this particle simulation, but the general estimation comes from the energy range, the energy ratio of the beam particles and the secondary particles, which is 10 to the 4, 10 to the 5, 10 to the 6.
And you make an assumption about where this discharge is happening, like how far away?
So it's not in 1D simulation, but if you play between numbers, this is pretty much the null surface.
Yeah.
This is where I agree with your term. Okay. So what does it do? Okay, so the theory of 1D discharge seems to be well established, but what happens in with the larger degrees of freedom, for example, 2D or realistic 3D discharge, as this can be responsible for some interesting intermittencies of the variation of the emission which are observed. For example, if we zoom in the position of this radio peak and trace it over like many hundreds of the periods as it's shown here, we can see that this position of the peak just drifts a bit in some sort of irregular way. And they explain what is called the subpulse drift. And the explanation for this phenomenon was hand-wavingly suggested by Ruderman and Sutherland in 1975, where they assumed that the discharge, this pair production, and how the driving of the radio waves happens not on the whole surface of the polar cap, but happens in the isolated sparks, which are shown on here, and it's separated by the vacuum region where there is no pair production. And these isolated sparks just drift on the surface of the polar cap in somehow regular fashion. How this might happen, the explanation is pretty simple. We have a conductor, a capacitor with the electric field in between. So this is how the potential look like if we include the boundary conditions at and the perpendicular to the electric field directions. But if we insert the conductor in the center of this box, then the potential in two free regions would drop significantly because of the boundary effects. And this potential might become that low that it's not longer capable of supporting the discharge and the pair production. But this is the question if it's true or not, because this is the stationary discharge. And what I saw in the previous slides, it looks like this actually should be intermittent. The bursts of the pair production are followed by the quiet periods with no electric field. And to answer the question, what would be these isolated sparks in the intermittent discharge? I present here the results of 2D simulation of the discharge, where we impose some distribution of the magnetospheric currents, which pretty much resembles the distribution of the currents for the aligned rotator when the magnetic axis and the rotational axis are in the same direction. And to avoid of the initial synchronization of discharge across the field lines, we split the polar cap into isolated patches, shown by this green dotted line on here, and populate them with dense plasma to ensure that there is no pair production.
So how are the sizes of the patches chosen? Are those just arbitrary or is there?
Yeah, just arbitrary. I split like in 25 ones in completely different. And we have initially 3 pages available for discharge, so the plasma is that low. The plasma density is that low that it starts forming the parallel electric field shown on the plots here. And at the later times, some additional patches become available for discharge, and because this happens at different moments, there is no initial synchronization. And whatever the synchronization across the field lines arises, this is consistent. And here's the example of the simulation of one of these discharges in the later times, where we see that there are already intermittent discharges at the high altitudes for the reverse or the negative current, when the plasma, similar to 1D, flies towards the star. And at the field lines which have the positive current, the potential is lower because of the geometry or the countersteering of the particles. And it starts with pretty much like stationary discharge, and the electric field here is stable. But what happens if the patches in between these available zones start connecting with each other? So we see that the electric fields communicate across the field lines, the charge starvation region. And first of all, the discharge switches to the intermittent regime, similar to 1D simulations, to 1D understanding of the figure. And also some of the synchronization arises. But because now we're in the intermittent regime, the lifetime of the unscreened electric field on each of the field lines is limited by the gap size. So this is just gap size divided by the speed of light. And if two field lines are separated by the distance, which is larger than this distance in between two discharges, the time when the signal can travel between these two lines, then these two field lines are staying desynchronized, which can be pretty much understood from the these complex shapes of the clouds. But still, the desynchronization isn't that large. But this is interesting. If the perpendicular scale, the perpendicular coherence scale of the discharge is similar to its size along the field lines, this means for the weaker pulsars, which are located here close to what is called the death line of the Pidon diagram, where the energy losses are pretty small, these pulsars are believed to have a very large gap, which is comparable to the size of the polar cap. And this should mean that there is no desynchronization across, so everything should be very coherent. And to check this, here is again the same distribution of the patches and the magnetospheric currents, but the different parameters to ensure that the gap size is large.
So what does this scale depend upon? Magnetic field strength or like the?
Yeah, pretty much the magnetic field strengths.
And the plasma density or?
Not really the plasma density, but so the formula for the gap size is here. So this weakly depends on the curvature of the field lines, because they limit how large Lorentz factor you can reach while you accelerate the period, and which determines the plasma density indeed, and the strength of the magnetic.
So we know that the PIC simulations, I think they overestimate the rate of the discharge.
Okay, I'll illustrate how this works when the discharge rate is more correct.
Oh, okay.
So yeah, coming back to this large gap, when the length of the potential of the unscreened electric field along the field lines is comparable to the polar cap size, we start with pretty much no discharge or the stationary discharge, and the electric field are just staying stationary and wait until the moment they can merge with each other when the potential increases, and it produces pretty much a coherent cloud of the secondary plasma across the whole field lines. And this switches again in the intermittent regime. And there is no field lines which do not possess the discharge. So it actually looks like there is no separation in between parts. The whole polar cap will be filled with secondary plasma and the wave production. And back to the question, as I said, these complex clouds of the secondary plasma give a hint what might happen with the desynchronization of the discharge, but is known from the observations of the thermal X-ray emission from the polar cap, which is probably produced by the bombardment of the surface by the ultrarelativistic particles from the beam, that we overestimate the rate, how often the discharge reopens, by a factor of approximately 1,000. Which means that there is some mechanism which keeps the discharge, the gap shut down for a while after the main burst of the plasma flies away. And here's the hint what it could be. So it's illustrated here. I play with some toy model where I toss some plasma into the beam which moves away, similar to the discharge, into the unscreened electric field, which is shown on the right here. And these two left plots show the plasma density, the total plasma density, which will be increasing to a factor of thousands of the multiplicity. And here's the zoom into the lower energies. And here's the phase space. So I start with the thermal plasma. And what we see in here, while this main cloud, the secondary plasma, the additional plasma propagates away and screens the electric field, some oscillations of the electrostatic electric field survive in there and push the particle in the opposite direction, probably creating this low density there. It's low density in with the ratio to the density of the main cloud, but still pretty dense, probably, to screen the electric field behind the cloud. And to simulate this effect of the long tails, I will present one more simulation where I add by hands the plasma into the moving window behind the secondary clouds of the plasma, and see how it changes the dynamics of the discharge. So if we start here, we see that there is this burst of the pair production, which are followed by the very long quiet periods with no electric field in here, and a large separation between these clouds. And what happens at the later times? Yeah, this happens in the later times. The field lines are still trying to communicate across the field lines, but they cannot communicate across patches because they live at a different time of different field lines, and they just don't know about each other, which splits the discharge into the segments of isolated spark of the localized sparks, but still the whole field, all field lines are related with the discharge, and there is no depth in lines. Okay, and the most realistic for the last 15 minutes is the most realistic is actually 3D discharge because the polar cap is 2D. And here I show the results of the simulation for the inclined rotator with the 60-degree inclination when the positive currents shown in red here and negative currents occupy pretty much half of the polar cap for each of the currents. And here on the left is the volume rendering of the secondary plasma density, where this plane at the bottom simulates the surface of the neutron star, and the color scheme shows the distribution of the currents. Here on the right, this is the video how the density evolves into different slices through the box. One slice is parallel to the surface of the neutron star, so the field lines are sticking out of the whiteboard of the desk. And here is the plane along the field lines. So here's again the electric field, and we start with 2 patches open, 1 page is in the zone of the positive current and 1 page in the zone of the negative current. And what we can see that for the positive current, the potential is too low to start the discharge immediately, and they wait until other sparks in between them, until other patches in between them become available for discharge to merge the electric field and to get the launch very synchronized large cloud of the secondary plasma away, which is will be shown in here in a moment.
Are these like artifacts something about the grid scale and the resolution? This like super square structure?
This is how I split into these sparks or the patches. So this structure. Each of these patches has like hundreds of this, so it's not really thin. Okay, so while we have the synchronized cloud, the secondary plasma on this, and the large gap for the positive currents, for the negative currents, it's all not desynchronized in a very chaotic structure because the gap size is small and the field lines are desynchronized on the scales comparable to the gap size. So this is all similar to 2D understanding of the discharge. Okay, what does it mean for us and for the produced high energy emission for the discharge? As I said, there was an old problem that it turns out that the density of in the immediate upstream of the current sheet is too high to explain the high energy emission of the highly energetic particles. But this turns out that from the global solutions of the pulsar magnetospheres, that the outermost field lines, open field lines, which actually connect with the current sheet and supply it with plasma and magnetic field, possess this negative current, which is again pushes the clouds of the secondary plasma towards the star, and only a small fraction of these particles flies away from this zone, probably, towards the current sheet. But now we have another problem, because in the previous time we had very high multiplicity of the plasma, high density of the plasma, and very little magnetization. But now the problem is quite opposite. We have a very low density of the secondary plasma, and this means that we have very large magnetization, and this means we expect a peak of the high energetic emission, not in the range of TeVs, but like rather thousands of TeVs or PeVs. So what might be actually happening there, that if the current sheet cannot be fed by the particles from the outside, it becomes responsible for itself, for feeding itself. So the hand waving scheme for this is that the current sheet does have some particles which are accelerated according to the mechanisms we discussed in the first part and emit this synchrotron emission. This synchrotron emission propagates away mostly and reaches the observer. So we see what the current sheet, how the current sheet actually shines. But the small fraction of this particle interacts with itself and converted into the secondary plasma, electron-positron pairs. These pairs in turn produce this soft synchrotron emission because they are not very energetic. And this soft synchrotron emission is upscattered by the ultra-relativistic particles in the current sheet and produces the inverse content signal, which is responsible for high energy emission. So this complex and heavy-waving structure can be split into some sort of semi-analytical model. We start with prescribing the model of the particle spectra and radiation spectrum based on our simulation from previous part. So we have a pretty shallow part of the spectra for the not very energetic particles which are weakly cooled or weakly affected by the synchrotron pooling. Then there is a decrease and the spectrum scales as gamma -2 for the particles which do feel the synchrotron pooling. And there is the radiation spectrum, which has the rising part until this energy of 16 MeV. This is pretty similar to what we see in the simulations. And then it lasts until this energy of 16 MeV and the ratio of the monetization of the gamma C. And then it falls. So what happens next is these particles are flying away mostly, but they interact. And they interact in a way that the most efficient interaction produces the very mildly relativistic particles with the Lorentz factor of a few, which is, and this injected spectrum is shown here in the dashed line. So it has the peak at relatively low energies of the sigma, like around 10. And this injected spectrum, first of all, it flies away. It has the injection of the additional particles, and it's being cooled by the synchrotron in the upstream magnetic. And there is a solution for this which balances all these three factors and creates the stationary distribution of the particles, which is shown by the solid black line in here. And this is the secondary particles. First of all, they produce relatively large multiplicity because there are a lot of photons, even though they wouldn't interact with each other. And this distribution has a peak at the very low Lorentz factor, which is probably 3 to 5 in here. And these particles produce the very soft synchrotron spectrum, which is shown by the green line here on top of the synchrotron spectrum produced in the current sheet. And we can see that the very soft emission is totally dominated by this synchrotron emission. And if these particles are upscattered by the most energetic particles from this part of the spectrum, then there is this additional inverse content signal. The good news here is that the position of the peak pretty much similar to what we expect, what we see in the observations. It's just a bit below of this 20 TeV limit, which might be determined by some how badly or how well the parameters are defined, and also by some beaming or the relativistic aberration. And the ratio of the signals of the peak luminosities in the so the GeV range of the synchrotron and the TeV range by inverse content is pretty much proportional to 10 to the -4, so the ratio of these luminosities, which actually coincides with the observations. So this Vela pulsar seems to be a pretty good playground to check the spheres. If this pair production of this current sheet, which supplies itself with plasma, is realistic or not. But there are more complex structures, which is like the crab pulsar, which has the spectrum shown in the dotted lines here, and it doesn't resemble anything very solid. So it might be because the pair production, the current sheet is that intensive that the spectrum changes very significantly between the emitted one and the one which escapes from the magnetosphere. And this is like the further project how this emission can be explained. And for now, I just stop with my takeaway points for the presentation.
think we have time for one or two quick questions.
Yeah, so you mentioned that for pulsars near the death line, you wouldn't expect to see drifting subpulses because the discharges should be,
That looks
they should
so,
synchronize.
yes.
And is that seen in the pulsar population?
Actually, this, they go, yeah. So this is the level backup slides, right? What is observed? So this is the PP dot diagram, which shows the pulsars with nulling or with drifts. They are pretty much concentrated reasonably close to the death line, where the gap size becomes comparable to the lights, to the polar cap size, which means that it cannot support the isolated sparks, and something else should be responsible for this drift subpulse.
So do you think it might be related to these extended return current
Could be
gaps?
responsible for some modulation of time, for example, for the police, but also for the somehow filtering.
All right. Well, so we still have a couple slots left for dinner, so please sign up. And you know where to find Sasha if you want to talk anymore or have other questions. So let's thank our speaker again, head to lunch.